I wanted to give you guys an answer key for the second packet of graph interpretation information that we gave you towards the end of this week. So this is the one that talks about a toy car, right? So what I've done here is I've already started by putting in the times just so that this moves a little bit more quickly. The rest of this I'm going to be doing this kind of live, so I might make some mistakes and have to change some things, but this is to show you how I would actually go through the process and solve it if I was doing this for a lab or for a test. So this says that it is the position of a toy car compared to a motion detector. We've got time and we've got position, so meaning distance. So the first thing that I always do, just to kind of help myself wrap my brain around this, I will draw a line right across the x-axis. And I do that really just to kind of call out where that zero is, so that I know exactly where it is. Being a position graph, I know that anything in positive numbers is in front, and anything in negative numbers is behind the motion sensor. Right now, this is assuming that you've got a fancy two-way motion sensor. We did not have one of those in class. So I've already gone through and done the times here. Miss Barry created this, and she was very nice in that she put the dots for every second, so it kind of helps you count there. And if you look over here, if the distance between the dots increases, right, whereas over here they're pretty close together, it gives you an indication of what your velocity would be. So that's just a little math tip there. If you were ever interested in calculating the velocity from a position graph, you know that the time that you moved the fastest was, right in here, because these lines are the biggest. But anyways, I'm getting off topic. So positive numbers will be in front, negative numbers will be behind. There's your zero line. So seconds 1 to 2, remember we always give a time, then kind of an action command, a verb, and then we give a direction or something like that. So this will be stand still. And where are they going to stand still? At 2 meters. Right? Because your position is not changing. You're at 2 meters here, 2 meters here, and 2 meters here. So then from seconds 2 to 6, you're going to move from 2 meters to 6 meters. Move from 2m to 6m. Then from seconds 6 to 9, I never labeled these. Oops. Hey, 3, 4, 5, 6. So in segments 3 here, you are again standing still. Jeez, my OneNote keeps moving all over the place. Stand still at, what is that, 6 meters. Okay. In segment 4, we're going to move from 6 meters. Ooh, we cross the x-axis. I always like to give myself a little x whenever that happens so that it calls it out to my attention here. Happens again over here. So what does that mean? If we get to the x-axis on a position graph, that means that we walk up to the motion sensor and then we go behind the motion sensor. Okay, so you walk or you move closer, right, from 6m to 0m, the motion sensor, then go behind ms from 0m to, we go down here to negative 4m. And that's, we're just going to throw in behind, right? We could even just do something like this, which is in front, right? That way you don't have to write it multiple times, and that way you're also proving to whoever's reading your lab or your test, hey, look, I do know that all of this is happening in front. If you've got it up here, we'll generally probably know, but now that we're talking about somebody being behind the motion sensor, it doesn't hurt to clarify when you're in front and when you're behind. So in segment 5 here, you're going to stand still. You're standing still at negative 4. Stand still at negative 4 meters. Then you're going to walk back towards the motion sensor, right, because you're walking from negative 4 to 0, cross over the motion sensor, and go up to 5 meters in front of. So walk towards motion sensor from negative 4m to 0m, then in front of motion sensor from 0m to, what did I say, 5m. Right, and I've got this in front here. Notice how I divide up negative 4 to 0 and then 0 to 5, right? I divide this line segment into two chunks. That way you can really call out the fact that you're walking up to the motion sensor and then going from behind to in front. If you just talk about negative 4 to 5, whether or not in your explanation or just your head or whatever, you might miss the fact that that crossing over this x-axis here means something important. So I always like to kind of divide this line up. We could almost think about it as 6a and 6b. A couple things that I forgot here. I included move closer here. I said walk towards here. This, I should have included a direction. Right? If we're moving from 2m to 6m, we are moving away. Right? See, I told you I'd make some mistakes. So now if we come down here to velocity, first thing, draw that 0 line. Since I already know that we cross the x-axis here, cross the x-axis here, I'm going to point that out. Anything going positive or negative, I'm also going to call out here. So in this case, since we're talking about velocity, if your velocity is a positive number, it means that you are moving away. And if your velocity is a negative number, that means you are moving towards. So that plus or minus gives you a sense of direction, right? It tells you, are we moving away from the motion sensor? Are we moving towards the motion sensor? In this case, negative doesn't mean behind. That would have to, you'd have to show that on the graph in a different way. Right now, velocity is just away or towards. We're not worrying about if you are in front of or behind the motion sensor. We should go through and number this stuff. 2, 3, 4a, 4b, 5, 6a, 6b. See, I'm just kind of calling those out. Now, within the steps, I'm still just going to have step 6, but it reminds me that this is a two-step step 6, essentially, that there's two different things that I need to make sure I talk about within there. So in this first segment, seconds 0 to 2, you're going to move at a constant speed of 2 meters per second, 2 meters per second, 2 meters per second. Or actually, I guess this is kilometers per hour. There we go. See, got to read the y-axis. So move at constant speed of 2 km per hr away. Right? And I'm going to make sure to include that because we're in the positives. So here now I'm going to go from 2 kilometers an hour up to 6 kilometers an hour. So speed up from 2 km per hour to 6 km per hour, again moving away. Now it's a constant speed of 6 km per hour away. So now this line is going to go down. If my velocity, if my velocity goes down, that means I'm starting to slow down towards 0 kilometers an hour. So slow down from 6 to 0 km per hour away, right? Because we're still above the 0 line. Then we get to the 0 line. If my velocity is 0 for an instant, that means I stop. Then if my numbers are now going from 0 to 2 to negative 4, those numbers are getting bigger. But they're negative, so that means that I'm moving away. So I'm going to speed up, or not away, towards. Speed up from 0 to 4 km per hour towards motion sensor. Okay. Segment 5, constant speed, it's a flat line. Constant speed of negative 4 km per hour, which means I am going towards. I should have a negative sign right in here, shouldn't I? Come on, Kalman. Now in number 6, we've got a two-parter. So we're going to go from negative 4 down to 0. So if we're going down to 0, that means we're actually slowing down. Slow down from negative 4 to 0 km per hour. That means we're going to stop for an instant, and then we're going to be starting to speed up, going away from the motion sensor. Speed up. 0, this goes up to 5. 0 to 5 km per hour, and we are again moving away. Okay, there's our final answer for what a velocity interpretation graph would look like here. So we moved on down to the acceleration graph. I've already labeled the times here, and I've already got the graph labeled up into 1, 2, 3, 4A, 4B, 5, 6A, and 6B. First step, as always, draw my line at the x-axis just to call it out. I'm going to put an x here, I'm going to put an x here. I'm going to label what it means to be above 0 and below 0. If I am positive acceleration, it means I'm speeding up. Speed up. If I've got negative acceleration, it means I slow down. Now remember, with our acceleration graph interpretation skills, we don't need to actually use numbers here. We just want to identify what the line is telling us, right? What is a flat line, an increasing line, a decreasing line, a negative line, a increasing negative line, right? What do those mean? We don't need to actually relate them to numbers. So I want to call our attention to this word here, which is what I've been using to describe by how much faster are you getting. So these jumps that we're talking about, what I'm saying here is, are you going from 0 to 1 to 2 miles per hour and you're making jumps of 1 mile an hour, or are you going from 0 to 25 to 50 miles an hour and you're making jumps of 25 miles an hour every second, right? So those jumps, if you remember my why are there two time units in acceleration video, if we're talking about 10 miles per hour per second, or 1 mile an hour per second, or 25 miles an hour per second. What we're talking about here is that this is how quickly this jump is occurring. This is how quickly this jump is occurring. So each of these 3 jumps are occurring within a second. But here your jump is just going up by 1. Here you're jumping up your speed by 10. And here you're jumping your speed up by 25. So I want us to think about this graph in terms of jumps. Because at least it makes sense to me, and I'm hoping it also makes sense to you guys too. So if we're looking at a flat line of acceleration, if it helps to look at the numbers, go for it. I'll start with looking at just the numbers to point something out. In this second, we're accelerating at 2 meters per second squared, at 2 meters per second squared, at 2 meters per second squared. So in each of those cases, even though we're flatlining, what that's telling us is that our acceleration is constant. It doesn't mean that we're not moving. It doesn't mean that our speed is the same. It means that our acceleration is the same. So if your acceleration is the same, that means that every second you're jumping by the same amount. In this case, 2 meters per second per second. So here we're going to just say that you have a constant positive acceleration, meaning that you are getting faster constantly, right, by a constant, consistent increment. So now here in our second line segment, we are first going up by 2, then 3, then 4, then 5, then 6. So in each of these cases, we're still speeding up, but every single second that goes by, we're actually speeding up faster. So our jumps are getting bigger. So it's an increasing positive acceleration, which means our jumps are getting bigger, or we're going faster or getting faster. Right? Weird thing to say, you're getting faster, but it means you are speeding up more quickly, which is another thing you could write down, right? There's lots of ways of explaining that line here. So in segment 3, this one here, once again, we have flatlined, but flatline an acceleration graph, which we've already done here, is just that means that we are accelerating by 6, 6, 6, and 6. So each of those seconds that goes by, your jumps are staying the same. They're staying at increments of 6 meters per second squared. So it's a constant rate of acceleration. We also include getting faster constantly, right? For A, let's look at this. Uh-oh, the line's going down. So are we slowing down? No, we're not slowing down. If we were slowing down, we would be in the negatives. Remember, positive acceleration means that you are getting faster. So if you're above 0, you're always getting faster. So then what can a decreasing line mean? Well, let's think about this in terms of numbers. First it's 6, then it's 4 meters per second, then 2 meters per second, and eventually 0 meters per second. We'll deal with 0 in a second. But my rate of acceleration is 6. So I'm getting faster by jumps of 6 every single second. Then I'm getting faster by jumps of 4 every second, and then 2 every second. So I'm still getting faster when I'm accelerating at 2. I'm just not getting faster as quickly. It'd be like this example up here, right? Here we're going up by jumps of 25, then only jumps of 10, then only jumps of 1. I'm still getting faster if my speed's going from 55 to 56 to 57 to 58 to 59 to 60, but it'd be a lot quicker if it was going from 60 to 80 to 100, right? Going up by bigger jumps. So a decreasing line means that I'm still accelerating, but I'm accelerating more slowly. So I am accelerating more slowly. We could say that I'm getting faster slower. Or we could say that I am accelerating, so positive acceleration, at a slower rate. But then what happens in 4b? So this is like a really long answer here because I've given you all the different ways of saying it. So this is all for 4a. So then I get to 0, which means that I'm not accelerating. Does it mean that I'm not moving? No. The spaceship that's moving really, really fast, but is moving a constant speed, is not accelerating, but still moving fast. So then I briefly stop accelerating, right, when it's 0, and then finally I'm in the negatives. This whole part of this line here, we're finally in the negatives. That was like me highlighting it. So for this 1 second, 2 second, I've got a decreasing line in the negatives. So those numbers are actually getting bigger, right? I'm going from 0 to 2 to 4. So that means that my rate of negative acceleration has gotten higher. So my rate, so I'm negatively accelerating, negative acceleration at increasing rate. Well, what does that mean, right? What does it mean to have a negative acceleration at increasing rate? So another way of saying that is you are slowing down faster or more quickly, meaning that how hard you're hitting the brakes, you're pushing harder every single second. So if I tapped the brakes, I'm going to negatively accelerate by like 1 meter per second. But if I push the brakes a little bit harder, it'll be by jumps of 5, right? I'll slow down from 60 to 55 to 50. If I slam on the brakes, I'm going to go from 60 to 30 to 0 really quickly. So that in that case, I'd be slowing down faster every single second. So here, since we're going from a rate of acceleration from 1 to 2 to 3 to 4 meters per second, that means that every single second that goes by, I'm slowing down more quickly. In segment 5, we've got a constant rate of deceleration, or negative acceleration, which is negative accel. So that means you're slowing down constantly. And then another tricky one, here our rate of acceleration is actually getting smaller, our rate of deceleration is getting smaller. It's going from 4 to 3 to 2 to 1 to 0. So that means that we are going to be getting slower, right? We are slowing down less quickly. Slowing down less quickly, right? Or you could say slowing down slower, right? To replace less quickly with slower. Either one of those will work. So essentially what that means is here we're like really slamming on the brakes. Here we're only tapping on the brakes, right? We're still slowing down, but we're doing it a little bit less violently, a little bit less quickly. Right? So you're slowing down less quickly, or you're slowing down slower, or you're slowing down at a smaller rate of deceleration. Then you stop accelerating. Then you actually start to speed up, and your numbers are going to get bigger. Your jumps are getting larger because you're going from 0 to 2 to 5 meters per second squared. So you're going to get faster. Or speed up more quickly. So this is why acceleration graphs are challenging, because there's kind of a lot going on, both in terms of, just because your numbers are going down from 5 to 4 to 3 to 2 to 1 doesn't mean you're slowing down. That's not your velocity. It just means you're accelerating less quickly. And as numbers get more and more and more negative, you're actually slowing down faster, right? Which is confusing to think about a negative number, negative numbers getting more negative, meaning that you're doing something more quickly, right? So acceleration is confusing just because conceptually, acceleration's a weird one. So as you can see for this fourth and final graph, I haven't done time segments here. And the reason that I haven't done time segments here is the reason that I love this graph so much. This graph is finally what we would be seeing as like a real life position or velocity or acceleration graph. If you think back to Lab 33, the graphing motion lab, none of our lines were ever perfectly straight, right? Even when we were moving away from the motion sensor, the line curved a little bit, right? And we were just graphing position, how far away we were from it. The line would curve a little bit, it would pause, it would do some weird bumps and, curving moves here. The reason for that is because we don't move in perfectly straight line segments, right? Whether we're talking about acceleration or velocity or position, it's impossible to move at a perfectly consistent flat line of velocity. We found that out in 33, B or C, when we were trying to match the graph that looked like that, right? You were trying to walk, and even when you were standing still, it was waving a little bit, and as soon as you started walking, it was like, woo, all over the place, right? And that's just because it's impossible to move at a perfectly constant speed. So in real life, things curve. In real life, it's not going to be perfectly flat lines. So that's why I like this graph a lot, because this is what it would, gets closer to what it would actually look like in a position or velocity or acceleration graph. So this video is already 24 minutes long. I could spend another 24 minutes just talking about this graph, because we could analyze it as a position or a velocity or an acceleration graph. But what I want to point out to you here, and what's most important about this graph, is that because it curves, you can't really say move at this speed constantly or accelerate at this rate, right? Because your rate of acceleration or your rate of velocity, or how quickly you're moving from 0 meters to whatever that is, 26 meters, is not constant, right? But what we should be able to recognize are trends or the patterns, meaning this line here is an increasing line. This line here is more or less a flat line. This line here is a decreasing line. This line here is a flat line at 0, a decreasing line, a basically flat line. It increases, it flatlines, it increases, it flatlines, it increases, it flatlines, right? So I could smooth this out and make it into, here's your rate, here's your perfectly flat line, right? Now that's not what really occurred, but the point that I'm trying to make here is that we can recognize that here's your increasing line. So while you might not be able to interpret it perfectly and say, okay, from seconds 0 to 5, do exactly this, you could say from seconds 0 to 5, your position is going to move away from the motion sensor. Is it a perfect flat straight line going from 0 meters to 26 meters? No. You move a little bit slower and then you move a little bit faster as you're doing that, right? Because we're looking at the slope of the line. It gets steeper and steeper. But if you're looking for the trends and the patterns, just like we have been the whole time, you're looking for a flat line, quote unquote flat, right? This is about as flat as you're going to get. If you're looking for a flat line, or a line that goes up, or a line that goes down, or a line that is flat, or down, or flat, or up, right? You can still recognize what these lines, and I'm putting that in quotation marks because they're curves, right, as life really gives us. You can still recognize these patterns that we've been talking about, and then you could still interpret when or what type of position, velocity, or acceleration is occurring within that curve. So this one, I'm not going to go through and do every single little specific detail because this graph has 1, 2, 3 different graphs in it. So this would be another 30-minute video just to go through this one. But what I'm going to tell you is to look for the trends and the patterns. And when you're looking for those trends and the patterns, you might not be able to explain exactly how to go from 0 to 26 meters to create this curve, but you would be able to tell in general how to move from 0 to 26 meters. Or if it were a velocity graph, how to speed up from 0 to 26 meters per second. Or if it's an acceleration graph, recognize that this curved but increasing line here is positive acceleration and that your jumps are getting faster. So you can recognize the trend and the pattern just like we have been the whole time. You just won't be able to give specifics, which is fine. So now you've got 3 answer keys, 1, 2, 3 for those graphs, and you've got a general method for looking at a more realistic graph and one that has curves and everything, and how you would interpret it in general and still recognize increasing and decreasing lines even if they were more curved.